Good morning, everyone. It's day 2. Thank you all for coming. I'm Sreenivas, and today I'm gonna talk about kernel level threat detection on Ubuntu. But most probably, I want to discuss more about more beyond the artifacts into the real time event correlation, all with using the eBPF. So, I just wanted to start it with a feeling that I guess most of the people in this room have had this. The feeling is that when we have spent our entire night logging through the lots of log and finally find that needle in that haystack. And that's exactly that says. Although SIN Sim is a fantastic history book. It tells exactly how you were bridged all after 2 hours after it had mattered. 2 hours after it has mattered. But we have to be honest to ourselves. But I'm not against these SIM tools or any other logging tools. They are essential. But we have to be at least honest to ourselves. We are log archaeologists. We are digital coroners where we have spent most of our time logging through these artifacts of an attack instead of focusing on the real attack itself. So, what's the fundamental problem? The fundamental problem is that we often confuse event with an artifact. Here, if you can see beside the event, what is an event? The exact event is the state change in the kernel. It almost happens at t0 seconds, and that's what the real compromise is. And if you can see, a process calls the executive to span the cell, we call it as an event as well. And at the time of conference, the kernel is the only witness we have. On the other side, we have the artifact, which is an oddity, a service. After maybe a few seconds later, after waking up, it writes a line to the hey, this event has happened into the log file. So this is the record of an event, not the event itself. So maybe after a few minutes, our log script detects it that something has happened. And in that meantime, the attacker would have lived in our system and would have done whatever he needs to be done. So if you are all agree that kernel is a place to be, then why haven't we done this earlier? So we had some few options as well in the earlier. The first one is uh, Linux kernel modules. So whoever wants here to pick that the 3 a.m. their custom kernel module has a small bug. Here small bug in a kernel is not a sick fault. It's really a catastrophe. It can create a very lot of chaos, and they are not portable or stability nightmare, and the security team is keeping the security risk by themselves. And the second, we have the audit which is a canonical solution, but it is famously high overheated, and there are too many complex filtering rules for it. And finally, it runs in the user space, which is slow, and at the end of the day it is just another logging tool. And third, we have the log parsing. By the name it says, it's just a log parsing, and it is very reactive. This is the end of story for log parsing. So what we have actually needed, we don't really need a tool. What we have required is an primitive. The new We needed a new architectural approach for this event streamlining. So for this architectural shift, we have something called eBPF, where eBPF is not a tool, it's a primitive, it's a programmable, event-driven, sandbox, and JIT compiled environment within the kernel itself. What does it mean by programmable? You can write this in your high-level language. So far, it supports Go, Python, C++, Rust, and C. And then it is event driver. It is not a polling. it is just attached right into your event. Then coming into the sandbox, it's the magic, which is a isolated environment, and then it is zip compiled. It's very fast and near native speed, and there are four main components in the eBPF. The first one will be the verifier, the second one would be the maps, third will be the JIT compiler, and fourth will be the API functions, which we are going to see in a while. So let me go through the observability pipeline of the eBPF. So first, it actually starts in the user space, where we will be writing the whole high-level eBPF code in our high-level language, and then we try to load that into the kernel, that eBPF bytecode into the kernel. But it is in that easy. In the next step, we have something called kernel verifier, which is very strict, just like the guards in the IISc. It is very strict. It doesn't allow as easy as possible. There are many restrictions. For example, no loops are allowed in the eBPF code. If there were any breaches, yeah, it will not let the code into your kernel. It will just crash and let you know that, hey, these are the wrong and you need to check. And if it passes through the kernel, then it will be zip compiled from the bytecode to the mission code. Then the program is attached into the event that you have created, and then it wait till that event triggers. So wherever that event triggers, this eBPF code loads into the kernel, and then it starts executing the perform. Then all the data that we get into the kernel while running this eBPF code using the eBPF maps, it will be transferred asynchronously to the user space, where we can see all the logs and details at real time. So let's sum up of theory. Let's see eBPF in action. So the first demo we are going to see is the all seeing wise. So we are going to just create a small eBPF function to check the entire system syscalls if it was opened or not. There's a simple logic in this code, and this telling the whenever the trace point syscalls happen, just bring the process ID, process name, and I'm joining the args to the argument vector, telling the BPF trace to watch out the argument vector and just fetch me the whole command that was executed. So if I execute that, this is how I'll get the data. This are lots of so much background radiation. If you can see, there's a payload was also worded into our program there. If you can see a PRD 2213, we may miss, but kernel has actually seen it. We'll see this in the demo just right now. So I have the two terminals here. In the terminal one, I have been installing the BPF trace. It's a sudo install. So I am pasting the logic code. Yeah, I have attached the eBPF code into the kernel. Then I am just simply doing the ls to check the directories in my system. And if you can see, I'm seeing the whole command that was I have entered over there. And let us go deep. When I try to get the more information, yet I'm getting the organizer. So let's be an attacker. Let us say I have found the exploit in the system, and I try to load my payload into that system. I'm trying to exploit that system. So if you can see, I am entering the payload evil.com. So here in this, you can see the payload was downloaded, pipe, and it has a sudo bash. So no log file has been written yet, but we already have a perfect high fidelity record of this attack chain. So this is how the real time you can get the data on the eBPF. So if you see, there's a lot of noise in the data. So in the next demo we are going to filter out the in this demo we are going to filter out to just get the information or the event trigger for the particular file that we actually care about. So here I'm just saying the file name, just saying the trigger. If the file name is HR, if someone try to open that, just let me know. And the rest everything is same. I'm printing the process ID, process name, and it is opening this file. So let us see in the demo that I pasted the command and then I haven't loaded my eBPF code. Then when I try to cat dot shadow file, now that eBPF program has triggered and it has opened actually. So I tried this in a cloud environment, but if you try in the local environment, you need sudo privileges, root privileges to get the to see what's actually inside the edge shadow. So when you try the cat at cd shadow, it has to fail. But these window shows even if that command failed, this will show there are someone who's trying to cat the shadow file, be alert. And then if you try the sudo, it will be showing that sudo is trying to open the etcd shadow file. So this is a kernel level honey point in one line. So we engineers and we know that there's no such things as a free lunch. It's still an engineering, and engineering is all about trade-offs. Whenever you first try with the eBPF, you have to hardly fight with your worst enemy, which is verifier. Verifier has a lot of hectic rules. Stack limit fight while by stack limits. No loops are allowed. So just like you fight with the guards here in the IASC, you have to fight with the verifier as well. But I promise you that you will love it once you get uh, used to it. And then next is compile once, run everywhere. So earlier, BP, for every kernel version, you have to recompile your eBPF code. But now we have BTF type format where it will be automatically changed. And the good news is Ubuntu kernel has inbuilt BPF type format. So just telling you to so that you will be aware about it. And next we are ringing from the firehouse. What does that mean? We are having a huge amount of data, like I have shown earlier. From there, it is almost very difficult to observe the logs, and your user space agents must be high performance to consume the data sent from the kernel to the user space without dropping the event through eBPF maps. So to mug up everything, for the years we have been forced to be a digital coroners, sniffing through the log files of an article. So it's now time to stop being a coroner and start being a sentinel. So what have we seen? Observe the events, not the artifacts. We have to be at the point of execution. Second, the artistructural shift, which is the eBPF, and eBPF is not a tool, it is a primitive. And yes, this is not a magic, it is right in your Ubuntu kernel. It is sudo apt install bpf trace. You can go home and try it. And yes, thank you.